Hi there, welcome again to SPIKY, the MATLAB-based graphical user interface for monitoring spike train synchrony. SPIKY was mainly designed to allow the application of our measures of spike train synchrony to discrete data. For instance, sequences of discrete events of which spike trains are one of the most prominent examples. However, the measures can also be applied to continuous data, such as EEG, after these data are first transformed into sequences of discrete events. Here in this movie, we show how this transformation can be performed within SPIKY by means of the event detector. The SPIKY package includes one example of a continuous dataset. So we first load the data from this example mat file. In this window, you can select the variable or the field which contains the data. In our case, this is already the correct variable, so all we have to do is to confirm the selection by pressing OK. These are 5 downsampled channels of modified EEG data that have already been used in Figure 10 of our 2013 paper. Similar to what is shown in subplot A of that figure, in the middle of this modified dataset, there is a transition from independent to identical channels. Now it is possible to restrict the time interval of the dataset and to select a subset of channels. Here we take just a smaller interval from the middle section and select just 3 out of 5 channels. To look at our selection, we press Update. It would also be possible to further downsample the data or to modify the amplitude scale. Once we are satisfied with our selection, we press OK. This is the point where it is possible to interactively select the type of event and its parameters. At the moment, local minima are selected as standard choice, and after pressing Update, one can immediately verify the result of the specific selection on the selected dataset. The events are clearly marked, and there are 3 ways how this can look like. Events can appear as superimposed spike raster plot, as symbols, maybe with a thicker line width, or they can be marked within the data themselves. Here we stick to the raster plot with standard line width. Then the 2 histograms show the number of events per spike train and per subinterval, respectively, which can help to verify that the selected events cover the underlying continuous data reasonably well. Currently, the other possible choices of events are threshold crossings, either upwards or downwards, and finally, local maxima. For each type of event, the event parameters control issues such as robustness to noise or require distinctness of the peak. They can be used to make sure that the selected events capture the essential behavior of the data. In this example, it turns out that at least one of the oscillations in the 3rd data channel was missed by the selection. Zooming in shows that for the selected parameters of the peak, some small noisiness disturbs the relative distinctness of the peak. This issue can be resolved by selecting a moving average which acts as a low-pass filter and eliminates the unwanted high-frequency noise. As a consequence, the event is correctly recognized. As one can see from this example, this kind of fine-tuning can be a very crucial step, since at the later stages it is these selected events and these selected events only that represent the whole dataset and form the basis for the subsequent synchrony analysis. Once we are satisfied with our choice of event, we finalize it by pressing Done. This way, we are back to SPIKY where the selected events appear as spike trains ready for analysis. From here on, we can proceed as usual. Pressing in sequence Update, Calculate, and Plot leads us to the dissimilarity profile for the spike distance. As you can see, the aforementioned transition from independent to identical channels is reflected in the spike trains as well. That's it for now. Cheers!